Hey everybody, this is Larry. This is me going with Q4 of the bi-weekly contest 114, maximum number of K-Divisible components. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's Q4, today's farm. Yeah. So this one, it's actually pretty. I like the problem. It's pretty cute. That's how I was able to get it in about 5 minutes. And it took, and a lot of that 5 minutes, to be honest, is just me kind of convincing myself that that's true. And you can watch the live portion afterwards, during the contest. But basically, for this problem, you're trying to divide, the you're trying to divide a tree or a graph that is a tree into connected components where the sum of the values are k, right, for each of the components. So that's basically the idea. And I think the hardest part about this problem is just really the visualization, because the code is pretty straightforward after that. And it's also one of those problems that I've been talking about lately with respect to if you look at just the code, it might not really make sense in a way, but you have to have a understanding of the problem. And so I'm just taking out my drawing pad to kind of draw it out. Oh, it actually came up to screen. That's actually a little bit weird, but okay, fine. I don't have to turn it on first. I do have to turn it on first. What am I don't know what I was on. Anyway, so yeah, so basically the idea is that and one of the preconditions of the problem is that the entire tree, the sum of all the values, is going to be divisible by k, right? So yeah. So you have stuff like this. I'm just drawing a random tree. I don't know, and it doesn't have to be a binary tree. So right. So there are a couple of ways you can think about it, but the core idea is going to be just greedy. What I mean by greedy, right? What I mean by greedy is that anytime you can how do I mean it by greedy? What I mean by greedy is that whenever you take off a branch where it is divisible by k, you want to. So the reason is because there's an invariant with that statement. And what I mean by that is that the invariant is that, okay, so this is a very ugly graph, and let me change the color a little bit. But let's say we kind of, disconnect it in some way, right? So let's say for obvious reasons, we only disconnect an edge. Let's say this one, if the branch, for example, in this case, it'll be these two, if this is divisible by k, right? So yeah, what does this mean? Well, we know that the entire tree is divisible by k, so that means that we cut it off here, and assuming that this is divisible by k, that means that the other part is going to be divisible by k still. So that's basically the core part of it, is this invariant that if you cut off a branch, then yeah, if you cut off a branch, then and it is divisible by k, if the sum of the elements are divisible by k, then you're still gonna, so because of that, now you have this like loop invariant, if you kind of think about it, or just invariant in general, where, well, now you can cut off here, and then like you could even think about this iteratively, right? Because now we cut off here, that means that this is divisible by k, but that also means the rest as well. So then you could just like cut off here, and then maybe even here. So then now you have this, and then so forth. And because of that, that will give you the answer, because every step of the way, it is divisible by k, right? And you can't do it and as long as you root it in the tree in any node, this should be good, because there's no way to kind of have an impossible situation, right? Because you're always doing it by the branches. What I mean by that is, like, if you cut off, I don't know, let's say this is divisible by k, and you cut it off, try to cut off this way, but this element might not be divisible by k, and then now you have a quote-unquote impossible situation, and also it's not maximized anyway, even if, or like, yeah, because you have components that don't sum to k, or sum to a number that's divisible by k, right? So that's basically the core part of it. And then once you realize that the sum of basically the sum of two components, if they're divisible by k, then they're also going to be divisible by k. And that's kind of how or the understanding is, and it makes the code a lot easier once you realize it. And I'll go over the code now, so that I gotta figure out how to remove it. Yeah. And yeah, so here the first part is going to be the very straightforward depth first search, and this is just, you know, sum or the total sum of all the subtree, right? And yeah, and this is just regular subtree stuff. Hopefully this makes sense. It's pretty straightforward. You could write this in a number of different ways, but yeah, this is a subtree thing, and this is just to convert it to an edge list, or an adjacency list to be more precise. Sorry, this is an edge list. But yeah, this is depth first search, get the total. So then how do you count it? Well, it turns out you can just do it with a loop, because basically what this is saying is that for every subtree where the total of that subtree is divisible by k, then you have one component, or you could make one cut above this to make it one component, right? So that's basically the, how this is. And of course, the root is always going to be also one component, even though you don't quote unquote cut above it. So that's why this will give you the exact number, right? Because, and in this way, you don't even have to cut in the quote unquote the right order. Though you could definitely have done it this way. You could probably put it here as well, with the increment, but I didn't think about it that through yet at the moment. But for example, if you look at this, let's say you have, you know, two cuts, right? Let's say you have these two cuts that, let's say that you have these two cuts that you have to do. It doesn't matter which order you do them in, it turns out. As long as you kind of make that cut, it should be okay. So that's why the loop is a little bit weird. But also, to be honest, like I said, you could have just wrote something like, let's say you have, you know, you can make times 0, then we'll go count. Or something like that, right? And that would also be fine. I mean, of course, you have to return it. But yeah, if you want to kind of think about it that way. But for me during the contest, I didn't quite do it. I didn't make the leap until like I thought that may be the case, but I had to convince myself for a few moments. So you could kind of see that in the contest video too. That's all I have for this one. This is linear time, linear space. There are a couple of places where it's linear space. The adjacency list, the sum array, and also just the stack size. So yeah. Obviously it's linear time because you have to look at each node once and each edge once, but number of edges is number of nodes minus 1. Yeah. That's all I have for this one. Let me know what you think. And yeah, you can watch me solve it live during the contest now. 1-1, is that right? Silly Larry. Solvable, but man, the 2 wrong answers is going to be a painful. Six people already got this, so that means that this is not going to be a great contest for me. All right. K 6, okay. Six people already got this. Wow. 12 people. Wow, people are getting this quick. I guess Leetcode is probably just not doing leaderboards anymore. which is fine, I guess. Okay. My good luck charm, naming everything Go. Okay. That table's messy. Okay. And then now what? Now. So okay. Is that true? What a silly contest. I mean, for me, like, there's a lot of silliness. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord if you want to see more. Yeah, stay good, stay healthy to good mental health. Let me know what you think about this contest, this problem, and everything in between. I'll see y'all later and take care. Bye-bye.